Ladies and gentlemen, place your bets, please.
I'll put 20 on black.
Same for me, on red.
Betting against me?
Let's see what Lady Luck has to say. Come on, red. I'm gonna win. I can just feel it.
Really? You know roulette is the most random game in this casino.
What do you mean? They're all random.
I'll explain later.
And it's 29 black.
Lucky you. Let's try the slots. Come on! Come on!
You know those don't work off how hard you press the button, right?
Maybe not, but it's more fun this way.
Old slot machines were mechanical, with an actual handle you pulled. But nowadays, the outcome is determined by a computer chip using a random number generator. The chip says whether you're going to win, not how hard you press the button.
You really know how to ruin a trip to Vegas.
And that's an example of randomness at work. There's a lot of randomness in casinos and in your digital devices. And while randomness in a casino is designed to eventually favor the house, not you, in your devices, randomness is supposed to help you, make you more secure. Welcome back to How Hacks Happen. This is part 3 in our series on random number generators. In parts 1 and 2, we talked about how randomness in games and devices sometimes isn't as random as it seems. In this episode, we're going to break down some of the concepts and technical terms around random number generators, otherwise known as RNGs. Don't worry, I'll keep it in plain English like I always do. If you haven't listened to parts 1 and 2, you might want to do that first. I'll be right here when you get back. Random numbers have been with us for a long time. If you've ever thrown a set of dice, you've experienced random numbers. A coin flip is also a great example of randomness. If you flip the coin once, you get heads or tails. But if you flip the coin 100 times, you'll get something close to 50 heads and 50 tails. So what are these random number generators used for? In the first 2 episodes, I talked a bit about the use in games and in our devices, but they're used in other ways in cybersecurity. For example, if you have a password manager and it comes up with these big random passwords for you, guess how it comes up with those passwords? An RNG, of course. And of course, in one of the previous episodes, we talked about how random numbers are basically encryption keys that get generated, so when you're doing web browsing, your connection is secure. They're also used at casinos and for generating winning lottery numbers. We want these things to be random, otherwise it would be cheating, right? So let's take a look under the hood of these random number generators and learn some of the terminology. And along the way, we'll learn some concepts too. The first concept I want to talk about is something called entropy. Now, entropy is a science kind of word, like you're not likely to run into it on social media unless you follow some physics people or something. But it means disorder or unpredictability, like consider one of those old temples that gets discovered in the middle of a jungle. It's half fallen down, the stones are all over the place, the plants have grown up all around it, and there's a big degree of randomness here. Which pieces of the temple have fallen off and the way they've fallen, and the way this plant or that plant grew up over here or there, and the size and shape of the stones that fell. These are all examples of the randomness of decay. The opposite of decay, in this sense, is predictability. Like when the temple was originally built 2,000 years earlier, the builders placed the stones in a particular way, and there was some predictability that the temple would be there that day, the next day, the next day. But then time went by, and wasn't so predictable anymore. But we're not here to talk about ancient temples. We're talking about random number generators. And in the context of cybersecurity, entropy means not decay, but unpredictability. Let's let's take a closer look at what this means in this context. One of the main features of randomness is that it's not predictable. And while it might seem weird to define something in terms of what it's not, this is one of the ways we do things in math. When we're trying to wrap our heads around something that's kind of intangible, like randomness, it can help to think about what it's not. And what it's not is predictable. So we can get a little foothold on how to create randomness by latching onto something that's unpredictable, like the way the stones fell on the ground when the temple disintegrated. Or, in a more modern context in our world of electronics, the perfect example of randomness is static, or white noise. All electronics make noise. If you've ever had an old refrigerator, you know what I mean. But everything from ceiling fans, coffee makers, lamps, curling irons, your computer, and even your own cell phone. Anything that runs on power, it makes a noise. You might not hear it, but the noise is there. This noise can come from vibrations in the circuitry, which varies based on the type of device, what it's doing at the moment, how much humidity is in the air, the temperature of the room, how long the device has been turned on, and 100 other factors. When you hear a hum or static coming out of a device, it might sound like it's continuous and always the same, but the hum or static pattern that you hear at any given moment is slightly different from the pattern you heard a moment before. To our ears, it all sounds the same, but at a microscopic level, these waveforms of this sound, they vary quite a bit from one moment to the next. The waveform for these sounds is full of these microscopic hills and valleys that you can't hear separately, and they're all over the place. It's basically random and unpredictable. And while we can't hear the hills and valleys, a computer can detect and interpret them, which makes these waveforms that come off an electrical device a great candidate for seeding a random number generator. There's one other thing I wanted to mention about noise. This term noise, it doesn't just pertain to something you can hear. It can even be something you see. In computing or in a visual field like photography or videography, noise refers to any kind of random pattern. If you take a photo when the light is too low and you bring the photo into your software and you try to adjust the exposure afterward, you'll get this pattern of different colored dots in areas that really should have a smooth transition from one color to the next. Photographers call this noise. Another example is the ripples on the surface of a lake on a breezy day. That forms a random pattern. If you wanted to replicate that look with a computer-generated image, you'd have to tell your software to get some noise from somewhere to make this random pattern. And here we come back to the word entropy, meaning unpredictable. We can say that some types of noise are unpredictable, and we describe those as high entropy. As in, the higher the entropy, the more random it is. Engineers also talk about what makes a good source of entropy. A good cybersecurity engineer is obsessed with good sources of entropy, and electrical noise, provided that it's from a source that really does make random noise, is a pretty good source. All right, so say we've got our great source of entropy. We're ready to generate some random numbers. So what makes a good random number generator? The quality of an RNG is measured by how it performs over time, after many, many numbers have been generated. You can't just flip a coin once and be convinced it's a random outcome. You'd have to flip the coin multiple times to test that it truly is a random coin flip, and that the coin isn't somehow weighted or tampered with to sway the outcome toward heads or tails over multiple flips. In the same way, you can't just use an RNG once and say, Hey, that number sure looks random to me. To test it, you have to generate thousands, millions of numbers, and then look at that list of numbers to test just how random it is. To be considered a decent RNG, the numbers produced need to be evenly distributed across the scope of possible values. Like if you have a random number generator that picks a number from 1 to 100, half the numbers should be above 50 and half should be below 50, and they shouldn't all be clustered between 40 and 60. They should be spread out, distributed. The RNG needs to produce a series of numbers that follow no detectable pattern from one number to the next. Like you can't just generate a great random number and then add 17 to it and say, here's my new random number, and then add 17 again. That would give you a predictable pattern that a hacker could exploit. So we don't want that. And the RNG has to have what we call a long period. That's the period of time before the cycle repeats. At some point, every RNG does start to repeat its pattern. But with current technology, we have RNGs that won't repeat for millions of years. So that's pretty secure. Anyway, that period of time before it repeats is a period, and you want a period that's like really long. Now, that's not to say that you won't get repeats with the random number generator. You might get some numbers that get picked more than once before others haven't been picked. That's okay. What we're looking at is a situation where the pattern starts to repeat and the same numbers one after the other are being spit out. And in fact, it's kind of expected that there will be repeats. You might think, okay, I want an RNG that generates 1 million or nearly 1 million different random numbers before it generates a repeat. With 1 million possible numbers, after the RNG generates around 1,200 of them, there's a more than 50% chance that it will make a repeat. This might seem counterintuitive, but this has been mathematically proven and is a parallel to this weird mathematical thing called the birthday paradox. The birthday paradox, if you've never heard of it, is this strange phenomenon that can be illustrated with a simple example. Suppose you have a bunch of people in a room and you ask each one to say their birthday, one by one, not the year, just the month and day. This means there's 365 different possibilities for what the person might say. Now, we're not taking into account leap year, or we're not going to factor in February 29th. We're going to assume there's no twins or triplets in the room. Just straight up, individual people, 365 days. So how many people do you need to ask before there's a repeat? Like where one person gives their birthday and it's one that's already been said by someone previously. Now, intuitively, you say, half probably? Like half of 365 is like 182. So when you get to the 180th person, we might start to see a repeat after that. But did you know you actually only need to ask 23 people before you get to a more than 50% chance that the next one will be a repeat? 23 out of 365. I know, it's crazy, but it's true. If you don't believe me, try it sometime. We did this experiment in my high school math class. We had 30 students and we had 2 repeats. We all thought it was a fluke, but it's actually backed up by solid math. I find the birthday paradox absolutely fascinating, and it gives us a lot of insights into how hard it is to design a really good random number generator that won't generate repeat numbers. Anyway, the same principle applies if you have 1 million possible numbers. After the RNG generates 1,000 or 2, the RNG will start to occasionally spit out a number that's already been used. So if a developer doesn't want this, what are they to do? Well, one thing is they could bump up the number of possible combinations to billions, many billions. And that would certainly increase the number of random numbers they can generate before a repeat, but it will also make the RNG slower. It might run hotter because of all the computations, and now the device needs a bigger fan to blow off all that heat. Another thing they could do is keep a list of numbers previously generated and check any newly generated number against that list. But that takes time too and computation. Or, they could just let it ride. Repeats aren't the end of the world, as long as the pattern of numbers doesn't repeat and it has a really long period before that happens. If an RNG has a period of millions of years, it meets that requirement for a good RNG. So maybe now you have a heightened appreciation for what these RNG developers go through. It's not like picking a random marble out of a jar or spinning a wheel. It's a lot of work. Let's look at an example that you might actually encounter in your everyday life. And that is the randomization function in Microsoft Excel. This function is called RAND, R-A-N-D. Excel actually has a few functions that produce random numbers, each with its own purpose, but they all work with the same RNG. We're just going to look at RAND for today. And the RNG that Excel uses, it's pretty good. It's unpredictable, has a long period, billions of possible results. It ticks all the boxes for a good RNG. However, most of us don't use Excel to produce billions of random numbers, and working with smaller numbers can give you results that don't seem random at all. Here's an example. A colleague of mine was once asked by management of his company to produce a monthly list of employees for random drug testing. The company had around 60 employees. They wanted everyone to get a random test around once a year. So my friend thinks, no problem. I'll just put all 60 employees in Excel, assign each of them a unique random number from 1 to 60, and every month I'll use the Excel RAND function to pick out 5 of them by number. This should work out fine, right? 60 employees, 5 per month, 12 months in a year. Everybody will get tested. Hopefully no one gets tested twice, right? Nope. Even with the randomness being totally random, by the time my colleague got to the 3rd month by which 10 people had already been picked, the probability of one of those 10 people getting picked again in the 3rd month is more than 75%. It's more of the birthday paradox thing. You only have 60 possibilities, you pick 5 of them, you're gonna have repeats very soon. So after a few months, this one guy got picked again and again and again, and he finally complained, which I would do too if I was off to my 3rd drug test in 6 months and no one else in my department had been picked at all. My colleague had to write a special algorithm so people wouldn't get picked more than twice in a year, and he had to get in there and see who hadn't been picked at all and manually choose them for one of the last couple months of the year. In this case, it probably would have been more efficient to do something more direct or manual instead, like sorting the employees alphabetically, but not by their first or last name, like start with the 4th letter of their last name or something, so it's not the normal alphabetical order, and then put them into the months, and that would be it. That would have been more random than the results produced by the Excel RAND function. So why did this happen? Does this mean the RAND function is garbage? Absolutely not. It has more to do with how small the numbers were. RAND is designed for larger population sizes and larger sample sizes. The random numbers it produces can be up to 15 digits long. If you were picking 1,000 employees out of 1,000,000, that might have worked better. But picking 5 out of 60, RAND had to stuff whatever random number it came up with into one of 5 boxes, and it's just not what it's meant for. Now, if you had chosen 5 employees per month over a period of 100 years, it probably would have evened out. But over a 1-year period, it's just not enough time. It's only 12 times that you're doing the sampling. So, yeah, RAND isn't made for that. Which brings us to another term we use when talking about RNGs, and that's bias. You're probably already familiar with the everyday definition for this term. It means showing a preference or leaning towards something. Like, when it comes to my cat, I am totally biased. He is the bestest, sweetest kitty ever. Even though he scratched me yesterday and this morning he brought me a dead rat. But, he's my beautiful boy. That's bias. In RNGs, bias means certain outcomes show up more often than others. And that's not a good thing in an RNG. In computing, bias can sneak in because of flaws in the algorithm or bad sources of entropy. And this can be bad because then attackers can predict the numbers more easily. The Excel rand function, that might have seemed to be an example of bias, but it's not. It looked biased because of the way we were using it, the small population and the small sample sizes. And that poor guy who got drug tested over and over, I bet he thought it was biased. For the RNGs that get used for cybersecurity, they're tested rigorously to make sure they're not biased. Speaking of bias, humans are more prone to bias than the best RNGs. Allow me to explain. Okay, let's do a little experiment. Right now, pick a random number between 1 and 10. Did you do it? Okay. If you picked 7, you're worth 33% of the population, with 6 and 8 tied for second place at 14%. Hardly anybody picks 1 or 10. So you could say that 7 is the most random of all random numbers. Try this with your friends sometime and see what happens. I did, and the only person who picked a number at the far end of the choices was someone who knows about random numbers and cybersecurity, and he knew where I was going with that question. So if you're ever asked this question at a party, you can kind of low-key set yourself apart as someone who knows a thing or two about random numbers just by picking 1 or 10. So that's Random Number Generators 101. You know all the lingo now. You can make informed choices when it comes to your devices or when trying to figure out how to get something random to work in Excel. If you want to learn more about random number generators, there's an entire chapter about them in my book, The Art and Math of Cryptography, available at Amazon.com. There are also a ton of YouTube videos out there about RNGs and the birthday paradox. Many of them really fascinating. Well, at least to me. Maybe not you, but maybe you. You never know. This is Michelle Bousquet from How Hacks Happen, signing off. Keep your random numbers random, folks.